Welcome to the Airvolt Deep Dive, the series where we break down the convergence of climate technology, digital media, and verifiable accountability.
Welcome back to the Deep Dive. Today we are tackling something, fundamental to city life, the air we breathe. Cities are amazing hubs, right? Innovation, progress. But they often come with this hidden cost. Toxic air.
It's a huge paradox. And the scale, honestly, it's kind of shocking when you look at the numbers. The WHO, the World Health Organization, says 99% of people globally live where fine particulate matter, PM $2.55, exceeds safe levels.
99%, wow. And the safe limit is tiny, isn't it? Like 5 micrograms per cubic meter?
Exactly, 5G middle. Most big cities, they just blow right past that number day in, day out.
So for this deep dive, we're not just going to talk about the problem. We're looking at a specific, maybe even radical solution. It comes from a feasibility study for something called the Airvolt AMPS. That's Air Monitoring and Purification System. The core idea, actually cleaning the air outside, actively.
Right, and that immediately brings up two massive challenges, which the study dives into. First, the technical one. Can you actually fight atmospheric physics? Clean air that's, constantly moving and mixing outdoors.
That seems like trying to boil the ocean almost.
It does. And second, maybe the bigger hurdle for any new city infrastructure. How do you pay for it? Is it economically viable? Because usually, clean air initiatives need huge subsidies or really strict rules.
But the sources we looked at suggest this AMPS system isn't just like a big filter on a pole. They describe it as this blend of engineering, data, even communication, designed to be, and this is the kicker, self-financing.
That's the claim. It's pretty bold. But yeah, let's unpack the physics first. Why is outdoor air quality so bad in cities to begin with?
Okay, so the study starts with what are called the urban trap. It's not just about emissions output.
No, not entirely. It's the city's shape, its geometry that traps the pollution. Think of dense downtown streets as urban canyons.
Urban canyons. Sounds dramatic, but I guess it's just tall buildings close together.
Precisely. And the key factor here is something called the aspect ratio, or AR. It's simply the building height, H, divided by the street width, W.
H over W.
Now, in most typical downtowns, that AR value is somewhere between 1.0 and 2.0. And when you're in that range, the airflow does something specific. It enters what engineers call a skimming flow regime.
Skimming flow. Okay, what happens then? Does the wind just skim over the top?
Sort of, but worse. It creates a single, large, fairly stable vortex inside the canyon, like a slow-motion washing machine turned on its side. So instead of fresh air mixing down and dirty air flushing out efficiently, that vortex just keeps recirculating the pollutants near the ground at pedestrian level.
Oh, okay. So the dirty air gets trapped right where people are walking and breathing.
Exactly. The study calls it the worst possible natural dispersion regime. It literally traps the pollution.
Which leads directly to where you put one of these AMPS units, right?
Precisely. The strategy is to target these specific stagnation canyons. These are canyons where the background wind, they call it Drawing 50, is too weak. It drops below a certain threshold. $2.
Okay, DUI 50, let's translate. Duty is like the minimum wind speed needed to actually clear out the canyon.
You got it. It's the coupling threshold. If the wind above the buildings isn't strong enough, typically below about 2.7 to 3.5 meters per second for a standard canyon, it can't break up that stable vortex. The air inside just stagnates. Those are the spots you target with purification.
And this focus on the ground level makes sense from a health perspective too. We saw data showing PM $2.5 meters drops off sharply with height.
Dramatically, by 60 to 80% between ground level and maybe 25 meters up. So the biggest bang for your buck, health-wise, is cleaning the air right in that pedestrian breathing zone, say below 5 meters. Why filter way up high when the worst air is down low?
Makes sense. Okay, so we know why and where you'd want to purify. Now the how. Let's talk about the AMPS unit itself, the tech. The first hurdle seems to be this thing called CADR, Clean Air Delivery Rate.
CADR local. Yeah, that's the fundamental metric. Think of it as the purifier's horsepower. The basic rule is the CADR from the AMPS unit has to be greater than the canyon's natural ventilation deficit. That's lambda V.
Okay, wait. Lambda V, is that just measuring how much cleaning the wind isn't doing on its own?
Essentially, yes, it's the gap. How much air exchange the street needs but isn't getting naturally because of that trapping vortex. If your machine's CADR is higher than that deficit, lambda VB, then you're actually making a positive difference. You're actively improving the air quality.
Right. So what's inside the box doing the cleaning?
It's a multi-stage process. For the tiny particles, the PM2 and $5, you've got serious mechanical filters, HEPA H13 cartridges.
HEPA H13, that's pretty high grade, right? Captures almost everything.
Very high. We're talking 99.95% efficiency for particles down to 0.3 micrometers. So very effective against the most dangerous fine particles.
But city air isn't just particles. There are gases too, like from car exhaust. NO-Euros, VOCs.
Right. So the next stage uses absorption or chemisorption media, usually activated carbon blends, sometimes things like impregnated alumina. These materials basically grab onto the gas molecules, pulling them out of the air.
And how much air can one unit handle? What's the power draw like?
A typical unit described in the study processes about 4,000 cubic meters of air per hour. That's roughly 1.1 cubic meters per second. To push air through those dense HEPA and carbon filters takes a bit of power, naturally. The fan uses about 0.66 kilowatts.
Okay, 0.66 kilowatts. Not insignificant, but maybe less than I'd have guessed. Now, the physical design seems clever too. It's not just sucking and blowing randomly. Where does it pull air in and push clean air out?
That's key. It draws polluted air in low at pedestrian height, around 1 to 1.5 meters, right where the concentration is highest. But then the clean air is exhausted upwards through an angled diffuser, tilted maybe 15 to 25 degrees.
Why angled upwards?
This is where it tries to work with the physics, not just against it. By pushing the clean air up and slightly leeward, away from the prevailing wind direction within the canyon, it's designed to gently reinforce that natural vortex circulation. The idea is to help lift the clean air out of the immediate breathing zone and prevent it from being immediately sucked back into the intake, avoiding reentrainment.
Interesting. Using the problem zone physics to help solve it. And these units aren't just dumb filters, they're smart, right?
Yeah.
Packed with sensors.
Absolutely. Each one is basically an IoT micro-observatory. It's constantly measuring PM2 and $55 temperature, humidity, even local wind speed.
And that data feeds back into how the unit operates, something about dynamic duty cycling.
Exactly. It doesn't just run at full blast 24/7. That would waste energy. Based on the real-time sensor readings, it can automatically adjust its fan speed, so rush hour traffic hits, pollution spikes. Or the wind dies down, trapping pollutants. The system ramps up to high flow mode. Later, if the air clears or the wind picks up, it can drop down. This dynamic operation saves significant energy. The study estimated around 25% compared to just running constantly.
That's smart efficiency. And the data isn't just for the machine itself, is it? There's a public communication aspect.
Yes, a big part of the concept. Each unit has a large digital display, like a 55-inch screen. A portion of that screen, maybe 30%, is dedicated to showing real-time local air quality info like the AQI and, crucially, a running tally of how much air it has purified, often shown in kilograms of pollutants removed.
Making the invisible visible. People can actually see it working.
And to ensure that data is trustworthy, the environmental performance telemetry, the pollution readings, the purification stats is secured using blockchain.
Blockchain, why?
For transparency and integrity. It creates an immutable, verifiable record, prevents tampering with the data. Essentially, it turns the environmental service, the clean air delivered, into a verifiable digital asset.
Okay, fascinating. The tech seems solid, it's smart, it's transparent, but we come back to the elephant in the room: money. Cleaning outdoor air feels like it must be incredibly expensive, a constant drain on city budgets.
And that's where the study proposes its most disruptive idea, the economic model.
This is the self-financing part. How on earth does that work?
It's elegantly simple in concept. The AMPS unit structure is designed from the ground up to also function as a high-quality digital out-of-home advertising display, DOOH.
Wait, so the big screen isn't just for air quality data, it's primarily an ad screen.
The majority of the screen real estate, yes, about 70% in the model described. They've essentially integrated the air purification hardware into a standard, modern digital advertising kiosk. So it's sited in high-traffic, high-visibility locations, not just for pollution, but also for eyeballs. Bus stops, busy sidewalks, transit hubs.
Okay, so you're turning an environmental device into a piece of revenue-generating media infrastructure.
Precisely. It converts the act of delivering verified clean air into a monetizable service funded by advertising revenue.
Did the math actually work, though? How efficient is the cleaning process in energy terms?
It has to be efficient for this to fly. The study highlights a specific energy efficiency metric, e-spectral. It achieves base 0.175 kilowatt hours per 1,000 cubic meters of air cleaned. That's quite low.
0.175 kilowatters 1,000 cubic meters. Okay. So let's put that into annual costs. What's the operational expense, the OPEX, for 1 unit per year? Mainly electricity, I assume.
Yeah, energy is the bulk of it. The modeling suggests an annual energy cost of around 460 euros per year per AMPS unit.
460 euros for a whole year of running this machine. That seems surprisingly low.
It is low relative to what it's doing. Now compare that to the other side of the equation, the revenue from that integrated DOOH screen.
Right, the advertising. What can a digital screen in a prime city location generate?
Based on typical programmatic advertising yields for DOH, they use figures around 9 to 12 per hour, and assuming a pretty moderate ad fill rate, say 60%, 1 unit is projected to generate approximately 47,300 euros per year in gross revenue.
Hold on. Did you say 460 euros in energy costs versus 47,300 in potential ad revenue?
That's the number from the feasibility study. That's the core economic argument.
That's not just viable, that's incredibly profitable. The energy cost is basically a rounding error, less than 1% of the revenue.
Exactly. The ratio is tiny, around 0.0098%, which means the gross margin, before you account for the hardware cost amortization, is close to 99%.
This completely flips the script on funding environmental infrastructure. It pays for itself, and then some. What about the upfront cost, the CapEx? How much is 1 unit, and how fast is the payback?
The estimated capital expenditure was around 9,500 euro per unit. And because that annual margin is so high, the simple payback period is exceptionally quick. We're talking 0.3 to 0.4 years.
So like 4 to 6 months.
Yes. The hardware essentially finances itself within half a year of operation.
That's just remarkable. It removes the biggest barrier to deploying this kind of tech at scale. Beyond the finances, though, how do they measure the public good, the actual value of the clean air being delivered?
They track 2 key public value metrics. First is straightforward, clean air minutes. For example, a unit at a typical bus stop might provide around 0.55 million clean air minutes annually for the people waiting there. It's a quantifiable ESG output.
Okay, a direct measure of exposure reduction. What's the second metric?
It's called the Public Value Multiplier, or PVM. This tries to capture the total benefit. They use conservative estimates for the societal health benefits of cleaner air, things like reduced healthcare costs, fewer sick days, lower morbidity risk, pegging that value at roughly 20,000 euros per year per location improved. When you combine that public health value with the private revenue and divide by the small operating cost, 460 euros, you get a PVM of 30 to 37.
Let me make sure I understand that. For every 1 spent operating the unit annually, it generates 30 to 37 euros in combined societal health benefits and commercial revenue.
That's the calculation, yes. It suggests the overall value creation is immense compared to the running costs.
Which makes deployment seem feasible pretty much anywhere, with bad air and foot traffic street canyons, bus stops, train platforms, maybe even tunnels.
The study confirms feasibility across all those scenarios. Anywhere you have trapped pollution and potential for digital display viewership, the model holds. It's the synergy. The technical need for local purification meets a viable commercial model.
Okay, let's try to wrap this up. We started with this paradox. Cities we love, but air that harms us. And we've looked deep into this Airvolt AMPS system, which seems to tackle the 2 big roadblocks. First, the physics that targets those skimming flow traps in urban canyons. Second, the economics that clever DOH integration makes it self-financing.
That's the core argument. And the vision laid out is ambitious. By 2030, they talk about a potential global network of maybe 20,000 AMPS units. Such a network, they project, could generate a collective societal health benefit around 452 million per year. And it would create effectively a real-time clean air layer, a new kind of urban data infrastructure monitoring and actively improving air quality block by block.
A fascinating prospect. This blend of environmental tech, data, and, well, capitalism, really. And it leaves us with a pretty provocative thought for you, the listener. When we face these huge global challenges like air pollution, do the solutions always have to rely on government regulation and subsidies? Or could models like this that are self-funding, maybe even profitable, be the key to scaling sustainable urban infrastructure much faster, making clean air not just a public good we hope for, but a measurable, visible, and economically viable asset?
Definitely something to ponder, especially next time you find yourself standing on a busy city street, maybe waiting for a bus, and you look up at that haze. Could the solution be hiding in plain sight inside an advertising kiosk?
Thank you for tuning in to our deep dive. Join our mission to breathe better ads and improve air quality in cities across the globe. Until next time,